Start sharing. Share computer sound, yes. Can you hear me?
Yes, I can.
It's just, I'm in the sharing mode. How to see my actual screen? Let me see. Share screen. Share screen now, yes. Oh, I was no.
Yeah, I can see you.
Minimize. Okay, I can minimize this. Oh, I see. So you can see my screen, right?
Yeah.
Okay, okay. Can you see the dark black ball?
Yeah.
Oh, good, good. We're here now. Right. So we spent hours on calculus, and we got something. So you do remember something which is by definition, which is this is called so if you have functions, so if you have functions, f for function, make it so f for function. Oh,
Yeah.
to think f for function, right? And sometimes we are interested in the first derivative, so we do something about it. We got something else. So this chemical. This is do you remember this notation df dx?
Vaguely. I don't remember what it was used
Yep.
for though.
Okay, we have to repeat that. So basically, what this notation, or simply use put the prime. You just put a prime here, or that will represent the first derivative. Okay, so this is a function. This is called a function. Okay, we have. I hope you have known something about function. Function is not English word function mean. It just means function is variable, right? The variable will depend on others. So what is the function? So basically, so the function is a dependent variable. So that is equal to dependent variable. In this case, we use f, right? We use f for function, okay, which is depend on what? Which is dependent on what? Of independent variable. So independent variable. Okay. Can we call this variable x, right? This independent is called f. So that's it. So the notation is just fx. So you say x, f is a function which is dependent on x. That's called a function, okay? And sometimes we just use y. Do you know why? We have explained that. Sometimes we just use y to denote the function. If you just use just draw a straight line, okay, draw a straight line here, can draw a straight line here. So this is y, and this is x. Okay, that was the invention of Descartes. So these coordinates, so it's very useful because that allows to us static function. For example, when x if the one particular value, right, you will use this formula. The basically also function is a formula. Function also is called a formula, right? So if you know this formula, then we should be able to draw that graph, right? Just by so if you work out one x, you got one dot, and get another one, okay? And sometimes you will say it's not a straight line. Sometimes it's not a straight line. Sometimes like this. So if you connect this straight line, you will get something continuous graph. Can you see continuous graph here? Okay. So what is a function? So function is just a formula, right? Which can be used to predict the known when one variable is given. Make sense?
Yeah.
So that's people spend a lot of time to define what a function is, but basically you have to get it familiar. If you studied physics before, you know that function just gives a formula, right? Which connect two or more variable. That's it. That's called a function. A good example is that I just give you example. This, of course, this is much simpler function. It's called linear function. Can you see?
Yeah.
Let's see, can you see this F is here? F is force, okay? So F is force.
Yeah.
Newton says the force equal to the mass multiply acceleration. Can you see?
Yeah.
Now in this case, either mass or acceleration can be considered as variable, right? So that is function. Now return to our study. So when we rewrite this function in this form, this will be called the first derivative. Okay, first derivative of function f(x). All right.
Yeah.
And that has many nicknames. That is called, first, the keyword instantaneous. It's called instantaneous. Okay. It could be instantaneous rate. Okay. Rate of change, right? Because obviously, if x doesn't change, they will give you a horizontal line, right? If it doesn't change, well, that is a special case. For example, I draw another function. If you say the function like this, you see that? That could happen. For example, if you measure, if you go to any car park, you see a car there, right? Then you just count the time. If you just, the car doesn't move, and the position will always give you one position. Do you agree?
Yeah.
Or near the door, at the corner. Do you understand?
Yeah.
So that is a special case. That is, in this case, the rate is equal to 0 in this case, in this particular case. Okay. So in this case, the rate or slope. Do you prefer slope or gradient? Which one?
Either's fine.
Yeah, either is fine. Okay, it's called a slope. One moment. I have to redo something. Okay. Redo. Okay, slope. Okay. Can call slope. And in this case, the slope is equal to 0, all right? Or equal to instantaneous slope. Okay, write down here, slope. Or people prefer to use a more formal name. It's called a gradient. Gradient. Can you see that?
Yeah.
So the first derivative represents the rate, okay, or slope, and that is useful. That's very, very important when you study the real problem. Sometimes you do need to find the rate. For example, I draw another diagram. Yeah. Does that allow me to draw a straight line properly? 2D. Oh, this is a straight line. So I draw. Oh, it's not a straight line. It's a square. It's just simply go to brush. Yes. I can draw without it. All right. I just draw another graph here. For example, this time, if you see the diagram looks like this, we go to something simpler, right? We go to say it's a straight line here. Can you see a straight line here, right?
Yeah.
Now this time, how about the slope? Can you work out the slope without a calculus? So basically, if you draw the horizontal line here, right, you will see the angle show up.
Yeah.
Now in this case, angle is not equal to 0, right?
Yeah.
So by definition, the tan alpha is also, so therefore another thing is called the tan alpha, okay? Because after all, tan alpha is a slope, okay? But every time you have put this adjective, instantaneous, all right? Now, in this particular case, doesn't matter if it's instantaneous or just average, because in this case, you can see no matter where you draw this slope, it remains the same. Do you agree?
Yeah.
So in other words, in this particular case, the slope or the gradient is constant. Do you agree? So the tangent alpha can also represent this kind of fraction. You can I just consider it's fraction, okay? df divided by dx, okay? It's fraction. But more in this particular case, and you don't have to introduce this abstract notation. In this particular case, how about tangent alpha? Well, have you studied linear equation in this case? what would be this function look like? Do you use a kx plus b? Can we do that?
Yeah.
Or some people prefer in textbook use mx plus c, right?
Yeah.
Same thing. Because in algebra you can use any letter to represent anything.
Yeah.
That is the essence of algebra. Now in this particular case, we don't have to use this abstract notation. We can simply use delta f and delta x. Do you know whenever you say delta, what would you how do you understand this delta whenever you say delta? For example, this is in this particular triangle here, you pick here, and the delta that would be the delta x. You can see this side. This would be delta x, and this side will be what? Delta f. Can you see that?
Okay.
So this is right angle triangle, right? So by definition, this in a straight line, and that is how to determine the slope. Can you see?
Yeah.
Same thing. Can you see the same thing? So there are so many ideas, but actually they are talking about the same thing. Okay. So in this case, you don't have to use this notation. This needs to be the abstract for you. All right. What is D? Well, D is for differentiation. Okay. D for differentiation. So when you start the what is I? I is for integration. Okay. Not integration. So there are two ideas you need to know when you start calculating. One is integration, and another is a differentiation. So it's a differentiation. Okay, D for differentiation.
Yeah, okay.
So you can but in this case we don't have to use this idea. We just simply write if you continue. So do you remember how we work out the tangent? We just measure this distance. Can you see? This is x. So this is y. Can you see? That's y. So basically we use f at x f1. So f2 minus f1 and x2 minus x1. Can you see that?
Yeah.
So in this case, these are x1. Is that diagram too small for you?
No, it's fine.
Okay, x2. So that is just this. I just remind you that's how we denote that. That's what we call f2. F2 corresponds to x equal to x2, right? And this would be f1. You see. So this interval is our delta f. Can you see that?
Yeah.
So it's simple. If you're dealing with a straight line, we don't have to use calculus, right?
Yeah.
Calculus became useful when you want to calculate, when you want to the formula for the slope, instantaneous slope, right?
Yeah.
For example, and I hope you can follow me. So for example, in this case, it's simple, right? How about the slope? If I use a different color for slope, how about say we have used green already. Can we use red?
Okay.
So that would be slope. Can you see? That would be tangent. Okay?
Yeah.
However, if you move to another position here, can you see that? And the slope will change. Can you see? When we say slope change, which means that the straight line, the slope of a straight line is changed. Do you remember the name for that particular straight line?
Tangent.
Tangent, yes. So tangent can be a ratio, or tangent can refer to a tangent line, a straight line. Okay,
Dr. Young, I'm gonna go get a drink of water.
Yes, take your time. Take your time. Okay.
Thank you. Alright, I am back.
Good. So I just draw this straight line here, right? The straight line here.
Yeah.
And in the special case, you will see a horizontal line. Can you see that?
Yeah.
When x is at the turning point, what you call the turning point, when you start the parabola, right? You see that in this particular case, can we call this? Can you say xt? Okay.
Yeah.
Or x3, whatever. Doesn't matter. Just indicate x is can we call the t, capital T. So that x here is what we call the turning point, right? At the turning point, the slope is 0. You agree?
Yeah.
So if I use a new notation, we just say that is x, the first derivative at xt, which is equal to 0. Can you see that?
Yeah.
All right, let's change the new page. I think it's a bit crowded here now. Any questions so far?
No.
Okay, you just listen to that, and you can just draw another. Oops. Make this one. Okay. Okay, another whiteboard, another blackboard. So let's go to brush here. Okay, let's continue. So do you remember last time we actually give the definition of this Newton's formula, this definition of the what is f prime, and also you can use the df dx, right? Which would put x here, first derivative, right? So by definition, so by definition, this ratio or this note or this slope, do you remember this? So this could be anything. I just write down, so this could be tan alpha, okay, instantaneous tan alpha, right? And so that is what does it mean. So, but in terms of the definition, we have to actually tell people, whenever you see this notation df dx, we actually mean a limit. LIM for limit. Okay, that limit says that if you have a finite interval for x for the function, okay, this ratio, and if you let this ratio change by reducing the delta x down to 0, okay, that's it. So that is what we have introduced last time. Now, if you go further, what is delta? You can write it down again. So what is delta fx in this case? So we need to draw the diagram, right? We draw the diagram. I draw the diagram. I have to do this particular diagram. Can we just consider the parabola this time?
Yeah.
Just parabola this time. So let's put the parabola here. Parabola here. So basically, by definition, if you want to know the slope, so you have to specify which is x. Okay. So because x, so that is a position where we are interested to know the slope. Okay. If I use this a straight line, so basically we need to draw. We need to find the slope of this straight line called the tangent, right? Called the tangent. It's called t for tan. So this at this particular position. But as we have discussed before, we can't do that without first of all to use approximation, right? So if we just let x increase to some numbers, can you say called h, right? Yeah. Or then we will see that we got a right angle triangle here, right? Well, anyway, to cut the story short, so basically we will get something like this. So f x plus h, right?
Yeah.
And then take away of fx and divide by this tiny interval called h, right? So where h is actually represent delta x, just for simplification purpose, right?
Yeah.
So in this case, we can also let h approach to 0. Does that make sense? It's just like a musical note. Do you agree? And they say, well, when you dim, you reduce the volume, right? Gradually.
Yeah.
And this notation just tell you, well, reduce the interval gradually down to 0, right? That's it. That's it. So that's the definition. Now let's just go to one more example. Last time we talked of can we just consider f, in this case, simple one. Can we just go to fx equal to x, right? So what does this, or even x plus 2, all right? Make it simpler. Now, whenever you see this function, what do you think? What is the graph? What does this graph look like? Or you can use yx if you wish.
Okay.
Yeah. The same.
Okay. Yeah.
Okay.
Same.
So whenever you see this equation, so what is the graph? What does the graph looks like?
Well,
What is the name?
The graph would look like it would be a straight line. Linear.
Yeah, linear. Okay, it's a linear. It's a linear function. That's the name come from, because the graph looks like straight line, so therefore it's called a linear function. Okay, linear function. So you know that for linear function, the slope must be the constant, right? And in actually, we without go further, actually we know the tangent or the slope in this case is what? Can you identify the tangent in this case? What is the tangent?
Tangent is.
Or slope. What is slope?
Slope is 1.
Yes, that's right. That's equal to 1. That's 1. Can you see? We know the result. Okay, basically know the result. But can we just use a general formula to prove that is true? Okay, pretend we don't know the slope determined in this way. So let's do it. Okay, so by definition, we just follow that by definition. By definition, let's do something. So what is the slope? Which one would you choose? Do you want to use a prime? Do you use a notation? It's simpler, right? And you can choose either use this notation. That's simple. Just use the prime there. That's it. That's called first derivative. So then we have to follow the definition. So we have to use a limit, right? And we have to use the fx plus h. Okay. What can we do? So the first term will be our, just copy that first, okay? X plus h minus fx divided by h, right? That's h approach to 0. Okay.
Yeah.
Let's move to shift this. We have more space here, so let's have some space, extra space. So we just started from here instead. So that's f prime now equal to a limit, okay? So in mathematics, we just whenever we invent the symbol, either use a single letter or just use the first 3 letters, right? So in this case, notation is just lim, right? For limit.
Yeah.
How about sign? You know that sign?
Yeah.
Yeah, that is sin, right? People think it's a sin. It's not. It's actually sign. Okay. So that is the convention we used in math. Now return to the question. In this case, what would be the fx plus h if we in this particular case f is determined by x plus 2? So in other words, x has been changed. You see?
Yeah.
X, and you have x and x plus. So in other words, so they have 2 intervals here. So one is fx, another is fx plus h, right? So basically, this is just a difference, okay? It's just like 4 rows in our arithmetic, right? The 2 difference f.
Yeah.
But how to write fx? How to write fx plus h? H eventually go to 0. Can we just use this formula here? Can we replace x by, so basically, can we replace x by, can we just replace x by x plus h?
Yeah.
Okay, so what can we get? We got x plus h, okay?
Yeah.
Or can you use a bracket? Okay, we don't have to, I don't need a bracket. And then the 2 there, 2 is there, can you see? In this way, I just make it sure and use bracket that we know that we have replaced x by x plus h as instructed by this definition. Can you see that?
Yeah.
That's so as a whole, this would be the fx plus h. Okay. Now how about second term? Second term is much simpler. How about second term?
It's just x plus 2.
Yep. But don't forget to use bracket, okay?
Yeah.
Because otherwise you're in trouble because there's a negative sign here.
Yeah.
All right. Now, can we simplify this one? We know that we're going to net h. Well, eventually we'll net h approach to 0, but not now, okay? Now, can we simplify denominator a little bit? Just by watching that. Can we simplify the
numerator?
Yeah, numerator, yeah.
Oh, it would just be h.
Are you sure?
Yes.
Yeah, right. Yeah, right.
And then the fraction would be just 1.
Okay, just 1. So we end up with this very simplified. So you put this 1 here, and the h has disappeared. Can you see that, right? H has disappeared. Okay. So what can we do? There's no h. So it's still 1, isn't it?
Yeah.
We can, because nobody noticed that. Okay. We just say net h go to 0. All right. This just diminish the volume to 0. Okay. That's it. It will not affect the mathematical expression. That's good news, right? Now, by the time we have done that, so what does that tell us? What does this result tell us?
It tells us the slope is 1.
Yes, exactly. That tells us, okay?
Yeah.
Yeah. So well, that's how you see. The general formula can also be used to dealing with very simple question. That is what called the self-consistent. So that any mathematical theory or physical theory must be self-consistent. So this definition is belong to what called self-consistent. Self-consistent, which means it's universal. Okay, you can either apply to the very simple function, or next step we'll try how to apply this formula to a more complicated function, right? I think last time let's just put the black color before we go. Okay. I think last time, just remind you that we have done that hard work. That means that we have proved something. That last time, remember, so last lesson, we have proved that given fx equal to x squared, right? Then we have that the first derivative of this function equal to 2x. Do you remember?
Yeah.
Yeah. Well, sometimes you can take some note, all right? That will help you to, if you take note, you will pick up, you will accumulate these things. So this is formula, right? And do you remember we rewrite, eventually we have, because we want to find some general formula, right? Do you remember how did we do that? So basically, whenever you see a function, okay, this is square, if you want to do the first derivative, right, then what you do is you put the 2 in front of that, right? And you copy the x, but this index must be take 1 away. You see?
Yeah.
Now, just remember, just first example, we say that if x equal to, say, x equal to x, doesn't matter that it's constant or not, right? So what would be the x to the first derivative we just have obtained? So this is first question, this is second equation, okay?
Yeah.
In this case, what is first derivative? Do you remember?
No, it's delta x over.
No, it's just 1.
It's 1. Okay.
Now, how do we rewrite this 1 by use this strategy, by use this scheme, or this just phenomenological interpretation? How do we get it 1? We can still use this 1. Can you see? We put this 1 here, but take 1 away. Can you see that?
Yeah.
So that's how you can rewrite this formula in this form. Can you see? I just highlight this keyword. Can you see? So this number, this is same as index. Can you see? This is the same as index. So index 2 and index 2. Okay. And every time you do the first derivative, every time you are asked to do the first derivative, you just take away a 1. Can you see that?
Yeah.
That is how you obtained this derivative. Okay. Of course, in both cases, we have used the definition, right? But mathematicians are interested in finding a general formula. But if you just consider this case, how about x? Consider another function. This time, let's go cubic, right? Let's go cubic.
Yeah.
It doesn't matter, just x to power 2, right?
Yeah.
Now, without use definition, just by using strategy, how can we find the, no, let's put this 3 here, okay? How can we find the first derivative of q? Can you guess? What is the index? Index 3, can you see?
Okay.
Do you want to try?
Sure, I'll try.
What would be the coefficient? What would be the number in front of the result?
Would it be 3?
Yes, you are right. Okay. Now let's just copy x here. How about index? What would happen to the index?
Well, it would be to the power of 1, correct?
No. Can we just reconstruct that one?
No,
Can we
2.
Yes, yes. Can we reconstruct this pattern here, right? Then we take away 1. Can you see?
Yeah.
Okay. Finally, what is the result? So that's just equal to 3x squared. Can you see? So can you see each time you do the first derivative, the power decrease, okay, the index decrease by 1.
Okay.
Okay, does it make sense?
Yeah.
Now how about this one? How about x equal to, say, to x 16 or 14, doesn't matter.
Yeah.
How about the first derivative?
First derivative would be 16x. No,
the number.
14x to the power of 13.
13. Can you see that?
Yeah.
Oh, great! You're in a track now, like a train, okay? Like a tram. Okay? In Melbourne, you got a tram. You take a tram.
Yeah.
Yes, tram.
Yeah, Melbourne has trams.
Yes. Okay. Now, give you a challenging question. Okay, how about fx equal to x squared plus xq? Now, how do we find the first derivative? So you got the sum of 2 functions. Do you agree? You got the sum of 2 functions. Okay.
Yeah.
So what can you do is you have to. This is just like algebra. You have to do it 1 by 1. Can you see?
Yeah.
Just like people in the queue, right? They're waiting for a barber. You cut the hair, right? You cut the hair 1 by 1. Okay, that's it. So that is can you put it right to the proper name?
So would it be 2x plus 3x squared?
Yes, 2x plus 3x squared. Okay.
Okay, so that's where
you are good.
Terms individually.
Yeah, you are doing the year 11 math now.
Great.
Yeah, it's great. So I think if you keep doing that, Because this is what we call analytical mathematics, right? You just use algebra, you follow the rule. And of course, and another exercise I will try. Can do this. I can just go to one more exercise. How about this time? Fx equal to 3x to the power of 5. What can we do with these numbers in front of it? How do we know what is the first derivative?
Well, wouldn't it be 15x to the power of 4?
Yes. 15 in respective. Well, forget about the number, right? That's right.
Yeah.
So whenever you say the constant, you just ignore it, right? So basically, or if you write down further, so whenever you say the constant, okay, the 3x to the power of 5, you just keep doing and just put a constant in front of that. So what is the reason we can do so? Have you think about the reason behind?
No?
No,
I haven't.
Okay.
No.
Before that, I have to consider another intermediate question. Do you remember that question? How about the function? Something very interesting happened. Do you remember this function we just talked about, right?
Yeah.
Okay. What is the first derivative? You follow this rule or the haircut rule?
Yeah.
Okay. What would be the first derivative? Can we just apply this formula here? You see?
Wouldn't it be 1? It would be 1x to the power of 0 plus 1 times 2 to the power of 0.
No, that is question to be answered. When you say the constant, okay, do you remember that scenario? When you say the constant, in this case, if you just consider two functions, right? F1, which is x, F2 is constant, right? Can we just consider as 2? So this F2, x2. So in the first one, the first function x is a straight line, right? From 0. Okay, the first function. So these are F1. It's F1. Can you see? How about second? How about F2? So if this is 1, 2, 3, is x. This is total function. Okay. So that would be 1 and 2. That would be 0. Okay. -1. Yeah. When you start high school math, you have to get familiar with this. Use this Cartesian coordinate all the time, right? Okay, how to draw the second part? How to draw the F2 in this equation? How to draw F2? It's constant. Do you agree?
Okay. Yeah.
How to draw a constant function? Special case. It's no change. It's just the same number all the time.
So it's just 2. Okay.
Now, how to draw this graph? My question is horizontal or vertical line? Can we go back? Oh, we can't go back. That is something
vertical.
We can't go. We can't. Vertical? Are you sure?
No, I'm not sure.
Okay, we draw the vertical. Okay, I just show what the vertical looks like. Do you mean the vertical? How about intersection about x? Where is the intersection?
It's 0, 0.
Do you want to draw the vertical? Which x should be interact with this? We're talking about. So we are talking about. Can we just different color? I hope you can still follow me. So basically, we are. Yeah. So F2 is constant. Can you see in this particular case, F2 this second function is just a constant. Okay, and you suggest to draw the vertical line, but my question is where are you going to put this here? Where are you going to put this straight line, vertical line?
Okay, so it would be a horizontal line.
Yeah, it could be horizontal, right?
Yeah.
Again, where are you going to put this straight line? Go back here. Where are you going to put this straight line? Can you use red, green color? Here, 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 where?
Well, 2.
2.
would
Yeah,
assume.
yeah, must be past 2. Okay, the past
Yeah.
2. In respect of the x is positive or negative or infinity. This is true for every x. Okay, so
Okay.
that's why we use this notation. If you're interested in this analytical math, I can teach you more. Okay, we can go to some statistic if you wish. Okay, so that's notation. So x is real. Can you see that? Which means x is a real number. That is a notation. Whenever you say
Okay.
okay, now in this case, as we have said, for this horizontal line, what is his slope?
Well, 0.
Oh yes. If the slope is 0, what about his first derivative?
Then the first derivative would also be 0.
Yeah. We are very quick learner. So whenever you see the constant, right, and you are asked to do the first derivative, you know it's 0 because it's a straight line. It is a straight line. Okay. Now don't confuse with this line. The vertical line. How do we represent this vertical line? By the way.
Wasn't it a slope of infinity?
Well, that's true. That is true. But how can we yet write and how we write the formula without use this infinity symbol? So what?
Well, wouldn't it be x over 0?
No, no, it's not. Oh, x over 0, right? What does it mean? No, this is undefined.
Okay.
That's just infinity, infinity.
Okay.
Now, if I want to write this vertical line, okay. So how can, yeah, that's a good question. So that is normally the straight line is equal to y equal to say m, use your notation, mx plus c, right?
Yeah.
So in this case, no matter what y is, x is constant, right? X can only sorry, that's right. X is always constant. Okay, that is something you cannot derive from this general formula. That's very interesting. You have encountered something exception. This is exception, right? Exception. So what is the property of this? What if you just consider any arbitrary point on this vertical line? What is something in common of all these coordinates? What is something in common?
Sorry, you cut out there for a second. Could you say that
Yeah.
again?
If I just put, we've just, this is a vertical line, right? If I ask you what, if you just see these are different point or coordinates on this vertical line, my question is what is something in common to denote this point on this vertical line? Say x, y, agree? What is something in common in this case? So y could be different, right? Y could be say y could be 1, 2, 3, right?
Yeah.
What is common for this point? What is x? What is the x coordinate?
2.
Yeah. Can you see?
Yeah.
So that is why when we denote the vertical straight line, you just indicate x equal to a constant. Can you see? This is y equal to a constant, right? Can you see? This is y equal to a constant. This is x equal to a constant.
Yeah.
Got it? Got it?
Yeah.
Wow, you're a quick learner. We can go further. Let's just draw another ball. So basically, we can deal with the combination of this question now. Can we do this simple exercise? So there's one more question. So there's question. And one more question. One. So how about so this is a given condition. We have fx equal to say 8xq plus 7 and minus make something. Just make a linear combination. Just keep doing same thing. Keep saying the x to the power of the. Oh, let's do something challenging for you. Okay. Let's do something challenging for you. How about x to do you if we write this notation, can you remember? Do you know that? Have you seen this notation? If you have x to the power of 5, you can rewrite it as a negative index. Have you started in negative index? Not yet.
No.
Are you in year 9 or are you year 7?
Yeah. We've studied. We haven't done negative index, but I know.
Yeah, you heard of that. Good. So how about how to rewrite a 1 over x if you use if you are now to use index?
Yeah.
So what?
Just 1 over the. It's 1 over the number without the negative index.
Yeah. So what number should I put
There
it here?
is
In this case.
1.
Yeah.
Negative 1.
Negative one. Negative 1. Okay. That's the only difference. Okay. You can
Yeah.
print. Okay. Now let's try. Can you work out the first derivative, please?
It would be 24x to the power of 2.
Yes, that's right.
Plus 7.
Square. Yeah. Plus 7. Are you sure? Plus what?
If the constant's right.
Yes.
Plus 0. Okay.
Okay. Now, the challenging. How about this one?
It would be minus 5x.
5 multiply x. Okay, to the index. Yes.
X to the index of -6.
Yes. Oh, well, you're a quick learner. Yes, that's right. Let's copy it again. The 24x squared. Forget about 0, right? Negative, sorry, negative. Oh, yeah, very quick learner. You don't have to wait until year 11. Let's just we do that. That can we say -5 here, right? And you got x to the power, say -6. Okay. Wow, you can do very fast now. And anything else we can do? I'll tell you another useful formula, okay? And but before that, can we just give you some trial for the product rule? Now, this is a simple function, okay? Let's just do one more different function. Have you seen this function, exponential function? Not yet. Have you seen the a to the power of x? Or in the special case, the base is e. Do you know the e value? Have you studied e value?
No, we haven't.
Yeah. E is an irrational number. It's called the Orner number. Orner number, right? Orner's number, which is just like pi. You cannot write it as in the form of fraction. That's all. Okay. Oh, you haven't studied that. Okay, probably will not go that far. Now let's just consider how about perhaps we can try one more question. How about if you dealing with a sine function? Oh, is that true? Have you studied sine function before?
Yes. It's opposite over hypotenuse.
Yeah. Have you studied this formula? That do you know this formula? The hint?
No.
I write down here for you. How about sine x plus a constant, x plus y? This is called the sum formula. Sum angle called the sum angle. Have you studied this? Have you studied the formula before? That equal to, I write down here, equal to sine x multiply cosine y plus cosine x sine y. Have you seen that before? No?
No, I haven't seen it.
Well,
no.
Probably we will stick with the polynomial, right? We'll stick with polynomial at this stage. And perhaps I will show how to do the, let's do some do something real. So question 3, okay. To find the turning point. Can you find the turning point? Find the tangent. Find the tangent. It's formula. Tangent 9. Tangent 9. Okay, tangent 9. Formula.
Yeah.
Equation or formula. Formula. Given the function, can we use fx for function? Fx equal to and 3x squared minus 5x plus 1.
Okay.
Yep.
Okay.
So what can we do? How about find the first derivative for this?
First derivative would be 6x.
Yeah, 6x. Yeah.
Minus.
Yeah.
5.
Yeah.
Plus 0.
That's it. Okay. That's it. Okay.
Yeah.
So this is tangent 9, right? So in other words, if you, in this case, can we use the y to represent this first derivative? So in this case, we put a t for tangent, right? So you got a linear equation. Linear equation. Can you see that? Okay. Okay.
Yeah.
That A. Question A. Question B. Can we find the turning point? Find the x t, right? For turning point, it's at the turning point, at the t for turning point. Do you know the turning point?
No, I don't.
So if you see, there's two scenarios here. Either you see this one, or you see this one. Can you see that? The turning point is here. Can you see that? In both cases, the tangent is horizontal. I'll give you the hint. Do you remember? We talked about that before. Right? This is called a tangent. It's called a turning point. Okay, it's called a turning point. Turning point.
Okay.
What does it mean? So when you say, if someone asks you to find the position of tangent, so basically you need to work out this x. Can you see? Actually, in our case, it's upside down. So basically, you need to work out this particular x t, right? This could be the y. Can you see that? Do you understand the question? We have just worked out the formula for tangent. Now, in this case, they ask you find a particular tangent at which the slope is 0. That is the question.
Yeah.
Okay, so what can you do? Can we use the previous result? Can we use the result from A? This question is A. That is format of question. Sometimes they ask you more than one question, but the answer of second question is connected, is relevant to the first one.
Yeah.
That is the case. This is the case at the moment. Okay. Now, tell me, how do we solve this problem? If you can participate, if you can write, are you able to write? Are you able to write on the screen? No.
No, I'm not.
No. Do you have the writing pen, like you can write on the the pad, or?
I don't actually.
Don't. Yeah, if you can write, well, in that way, just tell me. You just tell me, how do we solve this problem? How do we use the previous result to solve this problem?
I'm not sure.
Well, in this case, you have to get familiar with, right? So you have to know whenever you see this notation, okay, they have a bunch of the meanings, right? When you see the first derivative, it means the slope. It means the tangent. Do you agree?
Yeah.
Also the gradient. Do you agree?
Yeah.
Now, I have drawn the graph here. What is special for the tangent? when the tangent is horizontal straight line. What is so special about this turning point?
It means that the slope is 0.
Yes, yes, that's right. So in this case, slope is 0. Yes, that's it.
Okay.
How can we determine x? By assuming the tangent or first derivative equal to 0. Where is this question on this ball, on this blackboard? Where is the formula?
6x minus 5.
Yes, yes. Okay.
Okay.
So just let t this straight line. Let's just let is 6 minus 5 equal to 0. Can you see that?
Yeah.
That satisfies the condition. Okay, that's question. That is a big step. Okay, that's key step. So the rest is simple. So how about x? We got a 6x.
Well, x would be 5 over 6.
Yes, positive or negative?
Positive.
Okay. Okay, good. So in this way, we found the x. Can you see that?
Yeah.
At 5 over 6. Okay.
Yeah.
That's great. Yes, that's great. Because whenever because this arbitrary this is what can you tell me what is the form, what is the name for this function in this example? What is the name for this function?
That is
Yeah,
quadratic equation.
Yeah, it's quadratic function in this case. Okay.
Okay.
Fine. So that means a lot. Whenever you see a quadratic function, now you know. Once you say, "Give me the formula," right? Once you give the formula, you can always, without use algebra, you can use calculus by determining the first derivative in order to find the turning point position. All right.
Okay.
I hope that will help you to understand more about calculus. All right.
Yeah.
So I will because I record. Yeah, I will. You can watch this recorded video. Okay, I will because on the 9. Okay.
Yeah.
Okay, I'll see you next week. Okay.
All right.
And
See you.
if you have any interesting topic, we can discuss.
Okay.
Goodbye.
Goodbye.